Mm-hmm.
Okay. So, okay, we want to try to solve problem 1A. So we have two exact rows, A, B, C, D, E, with some maps, A prime, B prime, C prime, D prime, E prime, and 5 vertical maps, 2, 3, 4, 5. So, okay, we know that, okay, these two guys are monomorphisms, and this guy is an epimorphism. I guess I'll write on this way. So we want to check that middle arrow is monomorphism as well. So any suggestions about how to do this? So actually we just need to kind of pick an element here that maps to 0 and check that this guy is 0 as well. Okay, so any ideas?
So if A goes to 0 in C prime,
yeah,
then it also goes to 0 in B.
Okay, this is because it maps to 0 in D prime, and here we have monomorphism. Okay, yeah, indeed, A maps to the 0 in D.
So that means that it's the image of something in B, or yeah, something from B.
Okay,
yeah.
and
Yeah,
we
yeah.
have A tilde that maps to A. Okay.
We know that A tilde goes to 0 in C prime by commuting.
Yeah, it maps here to 0.
So the image of A tilde in B prime.
Okay, this is just F2 of A tilde is an image of some element B here. Okay, so it's B maps to F2 of F A tilde. Yeah, okay.
Because F1 is surjective, it has a preimage in A.
Yes.
And then little a, or yeah, A with no tilde has to be 0 because it's two boundaries together.
Each, yeah. Okay, cool. We have checked that that F3 is mono in assumptions of 1A. Okay, so okay, so now we want to well, kind of use the same arguments to solve problem 1B. So okay, just 1 second. I want to try to use Zoom Blackboard again. Just one second, please. Probably This is great. So yeah, I guess everybody can write down something here. Yeah?
Yeah, wait, you can also see this?
Yeah.
Oh, okay. Huh.
Great. So, well, let's try to use this thing. Okay. Probably it will be more, well, a little bit easier to connect to each other. So, okay, we have again A, B, C, D, E, A prime, 1, B prime, C prime, D prime, E prime, 5, 4, F3, F2. Okay, so now we know that these two guys are epimorphisms, and F5 is monomorphism. So we want to check that, well, this arrow is epimorphism as well. So, okay, any well, probably someone else instead, Danny can try to solve this problem. Well, do anybody have any ideas about 1B? Guys, come on.
So we should start with something in C prime and show that it gets mapped.
We want to find any preimage of, well, I guess you can try to write down something.
Yeah, so we can start with an X in here. We want to find X tilde.
Okay.
say boundary X over here. And I'll put a Y. And because F4 is surjective, there has to be a Y tilde.
Yeah.
This goes to 0 because boundary squared is 0, or just by exactness.
Yeah.
Then boundary of Y tilde is 0 by commuting, and because this is injective.
Yeah. Okay. Yeah. So I mean Y tilde maps to boundary, which is 0. Okay.
And then I don't know, that's it, right? Because if Y tilde is in the kernel of this D, then it's in the image of the previous one. So there's this X tilde as like a lift of the Y tilde has to exist.
Well, not exactly, because you actually you don't know that X maps to Y tilde, I guess.
That X tilde maps to Y tilde?
No, I mean not necessarily X tilde maps to Y tilde.
Okay, so something maps to Y tilde though.
Yeah,
right?
some maps.
So we can take some I don't know, some Z. Maybe there's no room. Maybe we can say boundary Z equals Y tilde. Where Z is in C.
Yes. Well, actually, you just know here you want to use some kind of property of, well, you should use that the square is commutative here. So you know that Z maps to Y by, well, on this along these edges. So it means that it maps somewhere. Well, this means that X minus F free of Z is a circle. Yep.
Yeah, okay.
So it means that there is some element B in B prime such that it maps to X minus F free of Z.
And then we can take a pre-image because F2 is.
Yeah. So now we can take B tilde such that F free F2, sorry, is B. And now I want to well, I guess my claim is something that
The boundary of B tilde maps onto X?
Well, let me see. Well, it could not be true because boundary of you mean it maps to X tilde or?
Yeah, I guess I mean B tilde maps to X tilde.
Well, I guess it is. Well, it is not true because, well, you know, you have here D of B tilde, and because this square is commutative, G of tilde maps to the difference between X and
yeah, whoops.
So, but you can take kind of.
Can we just add Z?
B tilde minus C or plus C. Yeah, this guy is maps. I mean, F3 of boundary of D tilde plus Z is X. Okay, is it clear or? Well, because, okay, so this is D, and this is F3.
Yeah, okay. Okay.
So are there any questions? Okay, so since well, except Danny, nobody is speaking. Please, if you want to ask some question, please just write down or use your mic. Okay, so and corollary of all this thing is the following. So if you have well, just let me. So okay, so if you have this kind of diagram and all arrows except F3 are isomorphisms, then F3 is an isomorphism as well. Okay, so is it clear or? So because of A, you know that F3 is a monomorphism, and because of B, F3 should be an epimorphism, therefore it is an isomorphism.
So all 5 of them being isomorphisms is actually like extra, right? We just need F1 to be an epimorphism and F5 to be a monomorphism?
Yeah.
But it's enough if they are. Okay.
Yeah. So I mean, I guess situations in which you can kind of use this 5 lemma to check that middle term is an isomorphism. Well, you know that kind of this extra data. I mean, so you know that all maps are isomorphisms, but not kind of monomorphism and epimorphism on the kind of left and right sides. So okay, now we want to use this to solve problem 2. So I will. So I guess I will send these I know these pages afterwards by an email, so don't worry about them. Okay, so now we have a map of a map of pairs F from XA to X prime A prime, and we know that the restriction is the both restrictions are homotopy equivalences. This means that X is homotopy equivalent to X prime and A is homotopy equivalent to A prime by F. Okay, so now and we want to prove that the induced map is an isomorphism on the level of homology. Okay, so we want to prove that star okay, any assumptions?
It seems like if we put together the long exact sequence and the 5 lemma, that I don't know, that's most of it, if that makes sense. So we have whoops. Oh my gosh. We have like a map like this. That's an isomorphism. And whoops. This is just a And map like this. And these are isomorphisms based on the given, because homotopy equivalences induce isomorphisms on homology. So these two are isomorphisms, and then like continuing the long exact sequence. This is in the middle, and then we have I don't know, star minus one of A, and if we put in like these, just like on the left, these are also isomorphisms, then this has to be.
Yeah. So, but here is one important thing. So we need to, well, actually, there is kind of, strong restriction on our on these isomorphisms. I mean, they should, well, we should obtain them kind of from the same map from X. Okay, is it clear what I'm talking about? I mean,
yeah.
so
yeah, they're both induced by this F.
Yeah. Yes. I mean, you have problem 2 in your homework, so you can look at it. So I mean, it is not enough to know that kind of each pair of this vertical arrow is an isomorphism. Yep, because, well, in problem 2, you know that both this map, and this map are isomorphisms, but still it is not true that the middle one is isomorphism as well. So this happens because in the case of problem 2 from your homework, these squares are not, and these and these are not commutative. Sorry? So,
okay, Ananya wants to ask. Yeah.
Why did you say that it's not exact? The middle one.
well, in problem 1, it is necessary to for all squares to commute.
Yes.
But if if they are not if they don't commute, the statement of the 5 lemma does not hold. So, well, in our case, they commute because they because we obtain them from kind of the same map, because you know that homology is the functor, and you have
because the top and the bottom row are exact.
I mean, so if you have a map of pairs, then you have the map of the long exact sequences.
Exact sequences, yeah. Like,
But
yeah, okay.
But well, if you have two different homotopy equivalences, then well,
Okay.
general.
That's okay. Okay. Thank you.
So can we look at like the chain groups instead, and kind of induce it from there?
Sorry.
Can we look at the chain groups instead of the homology? Like if we replace, I don't know, we replace all the H's by C's basically.
Well, I guess it is still well. I mean the chain. So you want to, well, there are still kind of, sorry. Well, you mean we should look at something like, well, C lower star of A, C lower star of A prime, C lower star of X, and
Yeah.
C lower star of X prime. Well, but still we need to kind of these maps. Well, this square is not commutative as well in the case of your kind of homework problem 2. Okay. Well, I mean,
Really?
we have solved the problem 2 from the kind of upper half. Yeah. So this is easy. We just use this. We just use the 5 lemma and the neutrality of the long exact sequence. Now, whoops. Well, yeah. In the case of second problem of your homework, this guy still not be will not be commutative. Okay, because these maps still should be obtained from the same maps. I mean, vertical maps should be kind of two parts of the same map. Okay.
So you're saying that the argument that I was starting to lay out only works like exactly under the conditions kind of that we had, that this map
Yeah.
this map was the restriction of like this map kind of.
Yeah. Almost. Yeah. Because
Okay.
there are kind of one different example in which it is still true, but there is
mostly. Okay.
another to prove this. So, but in general, well, I mean, what I mean, sorry. Yeah, I mean, in general, this is not true. So we need to kind of look for the commutativity of squares in 5 lemma. So okay, so I guess you have discussed the Meyer-Vietoris exact sequence. I mean, not discussed, but if you have watched the recording of the lecture, I guess Alexey Mislavich have told something about the Meyer-Vietoris sequence. So now we want to compute the homology of the torus using, well, Meyer-Vietoris sequence instead of taking its cellular division.
Mhm.
Okay, so what the statement? So what the Meyer-Vietoris sequence is.
We need to break the torus into like two subspaces that their interiors cover it.
Yeah.
Mm.
Well, I mean, the first thing I want to kind of you to explain me how the Meyer-Vietoris sequence works. So we have a space. So I will use another. So we have a space X. So now I want to write down something that is called Meyer-Vietoris sequence. What should I do?
So you have X, which should be the union of two subsets or subspaces. Like I cannot draw here. Okay, let's do it with my hand. Oh shit.
Yeah, well, it looks fine. So you mean?
But also, their intersection is not empty, right?
And then what do we have to do? Oh, so the Meyer-Vietoris sequence is, let me recall it. I remember there was a direct sum intersection. Okay.
I mean, are there any assumptions on A and B?
Well, they have to cover X, but that's it's already said here, right?
Yeah, but I mean, I guess.
And their interiors are, yeah, like the intersection of the interior shouldn't be empty. Like, should I put?
No, I guess you. I guess the easiest way is to say that both of them are open subspaces of X. So,
Okay.
because, as I remember, well, there is some strange example, kind of if you take two closed subspaces of X such that their union is X, then, well, then it won't work, I guess. So, but still, okay. So we have two subspaces of X such that their union is X, and their intersection is not empty. Okay, and
Then we have the homology. I don't know. Start of X. Well, this sequence to the intersection. And then
the arrows should maps to the other side. So you have natural map from, okay, so you have the map from intersection of A and B to X. Yeah, so you have just the inclusion of A cross of A intersected with B into X. So, and then you have by the neutrality, you have the map from A intersected with B to X. Okay. So, but I guess the answer is, well, that you have H of the intersection maps to H, well, to the sum of homology of each subspace, and it maps to H of X. Then go as one of A intersect with B. Okay. So yeah, so it should be.
I'm sorry. Yeah, I see.
Okay, so now we want to understand how to, well, what subspaces we need to take in the case of torus.
You can take like 2 cylinders. I will try to draw like
Well,
maybe,
I can try it.
yeah, like here, and one of them is like maybe this half. Well, they have to intersect, so the other one is this part. So you have the intersection are these two guys. I will put it in yellow. Yeah, I hope you get my idea.
Yeah. Okay, so I don't have enough color in my Zoom. So you want to take, so I guess this guy, which is, well, I will use red one instead of pink. So, and you have another one. Okay, so they both intersect, and their intersections is what?
Oh, these two cylinders. Okay, yeah.
Yeah, the intersection is just, well, you can, yeah, so intersection is two yellow cylinders, I guess. So we know their homology. Well, actually, we know the homology of all
circle, right?
Yeah, this is just, well, the intersection
Yeah.
in our case, intersection is just S1 disjoint union with S1. Well, it is homotopy equivalent to, whoops. It is homotopy equivalent to S1 union S1. And both both our parts is homotopy equivalent to just S1. Okay, so now we want to write down the Meyer-Vietoris sequence for this, let's say, partition of X. Okay, so does anyone want to write it down, or? So I can erase some. Well, I will erase this one too. So we have this sequence in the general case. So, and in the case of S1 process 1, so if anybody, if anyone wants to write down the answer, you are welcome.
I forget, the homology of a disjoint union is the product of the homologies?
Well, I guess the co-product, but
But
it's
yeah,
Okay, sure.
direct sum.
Sure.
So
I mean, anyway, like zero homology is the number of connected components, and you have two. So you can start with that and then go backwards.
yeah, of course. So, but okay, so this is just h star of x plus h star of y.
Okay, then I guess this page star.
Well, I guess you can write some any well numbers instead of stars
Yeah, sure.
because well okay, let's start from the obvious part. So is it clear that the homology in dimensions greater than 2 is 0?
Yeah.
Okay. So we want to compute kind of second and first homology of the
So this is 2, this is going to be 0. But, there's a lot of zeros. I guess we didn't really need to draw this one because this one is also 0, right?
This part. Yeah, I
well there stop. So you oh, you mean this one is okay, so
This one's 0. This one is also 0. Oh gosh. Okay. Can I call this T?
okay, yeah.
T. And this is 0 also.
You can try to draw the part to from kind of from right to left. So the part
Okay.
of
Like this term when star equals 1, this term when star equals 1 is just
yeah.
going to be z squared. Yeah. Just to save writing. And then we have H1 of T. And then we have H0 of the intersection. The intersection has two path components, so it's also Z squared.
Mm-hmm.
And then this piece, when star equals 1, is also Z squared because
Yeah, both. Well, you have two.
each of them individually are path connected, so they're both Z's. And then well, I guess this should be Z because it's path connected.
Yeah, okay.
So we know that because this is a 0, this map is injective. I don't know, F star.
Okay, so we want to describe, so you know that, well, since this map is injective, you know that H2 of T is the kernel of this map.
Yeah.
Of the map from here to here. So, okay, we should start from this part. So how to describe the map from, well, and you know that this is Z squared as well.
Mm-hmm.
Because this is just H1 of S1 is Z and H1 of S1 is Z, so Z equals Z. So
yeah.
You have a map from Z squared to Z squared. So, and what is this map? But to answer this question, we should kind of take, we should fix an orientation in our kind of parts of our X. Okay, so, well, here we have kind of this one.
So you fix an orientation and you send the blue part to one, let's say the upper one, and then all the red part to the lower, like each part of the intersection. I don't know how to explain. You cannot see my hands here.
I mean, well, I guess we should start from the fixing orientation. So I take orientation of the red piece like I have drawn. So I fix the orientation on the one boundary part. So this induces the one on the another. So I guess it should be this one. Yeah.
Mm-hmm.
Or sorry, I understand my. So I have here. I have this one. Yeah. Okay. So now I want to take the same orientation on the blue part. So I have these two things, and on and here on I want to take any orientation. So I will take the same arrows. Okay, so now my first z here. So I have 2 coordinates here. Yeah, sorry. So I have A and B. So to define this map, I should define where goes element 1, 0, and where should I map element 0, 1. So where I'm okay, so yeah, so now we want to describe this map. So again, 1, 0 is an element which is the circle here with the circle here with the given orientation. Oh, well, wait, sorry, I have, I guess. Well, sorry. Okay, so I said something wrong. So sorry. So this z squared is not the sum of these 2 parts, but it is the homology, first homology of the intersection. So I want to describe the map from here to here. Okay. So is it clear or?
Yeah.
So I mean this sum is just first homology
The
of
intersection, yeah.
intersect with B. So I want to describe the map of the induced map of the embedding of these 2 yellow cylinders into, well, my 2 parts of my torus. So okay, first one, well, this cylinder corresponding to an element of 1, well, to an element 1, 0, this one to 0, 1. So
does 1, 0 go to -1, -1?
okay, so 1, 0 maps to, oh, I will erase here. So I have 1, 0 maps to -1, -1. Okay. And 0, 1.
Goes to 1, 1?
To 1, 1. Okay. So I have, obviously, I have sorry, I have the kernel in this case. Yeah. Is
Yeah,
it clear?
it's the diagonal inside Z2?
Yes. So all elements of the form AA in Z squared is in kernel this arrow. So therefore, we have H2 of t is z. Okay. So now we want to describe H1 of t. Whoops, sorry. So okay, so we have so now we know that this map well, we can quotient this map by z and the embedding into H1 of the torus. Okay, is it clear? This z is just the co-kernel of this map.
Sure. Yeah.
Okay, so we know that H1 of t is at least z. So now we want to describe the kernel of this map. Oh, whoops, sorry, of this map. Okay.
Yeah.
So okay, well, this is H0 of the intersection, and this is H0, well, the direct sum. This is H0 of A plus H0 of B. Okay, so what is this map?
This is the same map from
Sorry?
like the same map circled in blue, like the one we were looking at before.
Yeah, but you mean that we have 0, 1 maps to -1, -1, and 1 and 1, 0. Well, sorry. So can you say it again, please?
Yeah, I was thinking that the like this map, the one that's circled in blue, would be just.
Oh, okay. Well. Mhm. So okay, let's see. So, well, I mean, I guess on the level of the components, you have kind of only positive maps. Okay, so I mean, so in this case, it doesn't matter, but I guess answer is, well, that both 0, 1 and 1, 0 maps to 1, 1 in this case. Because this map just says that you have the path component that maps to path component, but you're kind of you don't have any, well, on the level of path components of your space, you don't have any orientation. Okay. But well, in our case, it is it doesn't matter, because anyway it has the one-dimensional kernel. So anyway, if this guy maps to 1 1 and this guy maps to plus minus 1 1, anyway we have the kernel and it is Z. Okay.
Yeah.
So therefore we have the following exact sequence. So Z embeds to H1 of T. It surjects to Z. Okay, so well, therefore, since there is no kind of non-trivial extensions of Z by Z, we have that H1 of T is Z squared. Okay?
Yeah.
Cool. So, any questions? So, okay, now we have about, well, 20 minutes, I guess, and 2 problems left. Okay, so we want to compute the first homology of the genus G surface. So is there any ideas how to solve this? So let us start. I guess we in this, well, in the view, what
Can we use like, oh no.
can we use? What? Sorry.
Nothing, I was just thinking, but no, haven't tried yet.
Well, let us start from the. I guess we should start from pi1 of Sj. So can anybody write down the answer?
What is S sub G?
This is just T connected sum with T, connected sum with la with T G time.
Ah, okay, thank you.
So this is just oops, sorry. We have 1, 2.
Is it? Z G times. Yeah.
Oh, you think G times?
Yeah. Sorry. Yeah.
Could you?
2G. Sorry.
Nice.
Well, you mean this is answer for pi1 or pi or H1?
I guess pi1.
Well, but
No, it's free generated.
Yeah, but I mean that the pi1 of this guy is not almost always it is not a billion.
Oh, whoops. Oh, it is. Oh no, it is like free product of Z.
Not exactly. So let us see. So let us consider the case when G equals to 2. It is enough for me to draw. Okay, we have this polygon. So this A1, minus 1, B, 1, B1 minus 1. Here we have A2, B2, A2, -1, B2, -1. Okay, so this is my kind of cellular structure of this guy. Okay?
Yeah.
Yeah.
So how to read the pi1 from this picture? So you have kind of 4 edges. A1, A2, B2, and B1. Okay, so P1 is a group with, with 4 generators, namely A1, A2, B1, B2.
Such that, yeah, the relation. Oh.
And the relation, we have A1, B1, A2.
Oh, the product of all of them must be
0.
Yeah, okay, 0, yeah.
Okay, is it clear or? Well, this is just the consequence of the Seifert Van Kampen theorem.
Mm-hmm.
Okay, so you have the generators which corresponds to the 1 cells and the relations which corresponds to the kind of words on 1 cells of your cellular complex. Okay.
Mm-hmm.
Yeah.
Okay, so now you have discussed, I guess there was something on the lecture such that, well, H1 of any space X is isomorphic to P1 of X modulo the commutant subgroup. Okay, this is just an abelianization of P1. Okay, so now we have this group, this group, and we want to describe its abelianization. So in general, you should take the free abelian group with this with the given set of generators, and and apply all relations that you have. So, but let's see what is this relation.
Well, that relation is always true if they commute.
Sorry?
Their relation is like trivial if they commute, right?
You mean this particular relation, or in general?
Yeah, isn't it? If A1, B1, A2,
Yeah,
B2.
yeah. Of course, because the commutator of two any elements in the abelian group is 0. So
Yes.
we should forget about this this all relations on of commutativity. So therefore we have H1 of Sj is just, well, okay, so we have H1 of S2 is just Z to the power 4. And in general, we have H1 of Sj is just Z to the power 2j, which is this. Okay?
Yeah.
Well, you have kind of a little bit more tricky example in your home task. So you have to compute first homology of the connected sum of RP2 with Sj. So, but I guess you can start from the Klein bottle. So this is just RP2 connected sum with RP2. Okay, so and the last problem for today is problem number 5, and we have about 5 minutes to solve it. So we have simply connected and dimensional CW complex with trivial homology, or except the higher, and we want to prove that X is homotopy equivalent to the wedge of spheres. So we have X, P1 of X is 0, H K of X is 0 if K less than N. And I want to prove that X is homotopy equivalent to wedge of S and alpha. Okay, so any ideas about how we can do this?
So it seems like the condition tells us that it has no like K cells for K less than N.
Yeah, but well, this, okay, so indeed, this is only thing we need to, oh, sorry, and we have dim X.
Yeah, that too.
Okay, but this is only thing we need to check here. Okay, so let's try to start from the beginning. We suppose that we know only, so suppose, sorry, we know only that P1 of X is equal to 0. Or, okay, so what can you say about the cellular structure of X?
It's 2 skeleton is just a point, or is it homotopy equivalent to a point?
I guess 1 skeleton. Well, because
So we have,
if you can take just 2 sphere and its 2 skeleton is whole space, but its 1 skeleton is indeed just 1 point. Okay.
I was thinking about the pi k of X is isomorphic to pi k of the k plus 1 skeleton of X.
Yes.
But the,
So, but still you are right. So I mean, we have that sk1 of X is just 1 point. Okay.
mm-hmm.
Okay. So this is a hint for you. So, okay, but what do you know about the Hurewicz theorem?
That we're going to prove it next lecture.
Yeah, but I guess you know that, do you know the statement of, or?
I think I may have seen it somewhere, but I don't think we have said it in class.
Oh, okay. So this this problem is about Hurewicz theorem. So I will state it now, but well, okay, you will discuss the proof on the lecture. But for the moment, so now, okay, this is theorem, which is due Hurewicz. So the statement is the following. So we have X is simply connected CW complex, and then we have the following statement. So the first non-trivial homotopy group is isomorphic to the corresponding to the corresponding homology group. Okay, so it means that if you have P1 of X equal pk of X equal to 0, then pk plus 1 of X is isomorphic. Oops, sorry. pk plus 1 is isomorphic to hk plus 1 of x. Okay?
Okay.
And this isomorphism is natural on the for the maps of CW complexes.
Okay.
Okay, is it clear or? Well, I mean, not clear, but do you understand the statement of the?
Yeah. So then all the homotopy groups in our problem have to be trivial up to n.
Yeah, so we have from here we deduce that by which theorem pk of x is equal to 0 for k less than n. Okay. So, and I guess we either discussed it in the previous classes or there was a problem in the problem sheet that if you have first, well, I mean, if your CW complex is connected and you have first K homotopy groups is trivial, then your K skeleton is homotopy equivalent to a point.
Yeah, that's good. That feels true. Yeah.
Yeah, you can do the same. Well, the proof is the same as in the case of pi1. So okay, so let us discuss the case of pi1. So how to prove this this implication?
Could we just do it by no?
Well, okay, so you have one point which is 0 skeleton of x. Okay, and you have some cells such that well, you have some one cells of your uh, of your well, in you have some one cells in x. So because so I mean, suppose that sk1 of x is just wedge of some circles. Okay.
Okay.
So, but since your since your x is simply connected, any loop can be contracted to a point. So there is kind of two cell that attached to this that is attached to each loop of this wedge. So you can you can contract these two cells to the point and then extend the homotopy by Borsuk-Lamb. something is not clear here. So please ask the question.
And we can look at when there's just one point, because if there were more points, we could kind of like look at a subcomplex with only one point and then move it out.
Yeah. Okay, so start from, okay, so we have several 0 cells, okay?
Yeah.
So we have the problem that if you have,
yeah, that's right.
so you have some, if X is path connected, which is our case, then you can, then path connected, it's one skeleton. So there is the path from each point to another, and you can take its maximal tree, okay? So your one skeleton is the graph with some vertices, okay? And you can take its maximal tree, and then you can contract it because of Borsuk-Lamb again.
Yeah.
So, okay, so you obtain so from this case, you have this, well, our first case. So you can always assume that your CW complex has only 1 0 cell. Okay.
Mm-hmm.
Yeah, I
So,
have a question here.
Yeah.
So the pi1 of x is 0 just implies that every path is non-homotopic and not contractible, right?
So can you say it again, please?
So the pi1 of x equals to 0 implies that every path is non-homotopic.
You mean homologic to, yeah.
Yeah, but not contractible.
Yeah, of course. Well, the path is always contractible because this is just a segment of your, well, the segment is always contractible because this is just this is a segment. So this is just unit interval. It is homeomorphic to the unit interval.
Wait, please.
So you mean that, okay, so we have the, I guess I have understood the thing you're asking about. So suppose we have kind of 3 points and 3 paths from, so suppose that our one skeleton is this guy, yeah?
Yeah.
So but still there is a kind of, so this is one-dimensional graph. Yeah, so it contains maximal tree. This is the maximal path connected subgraph such that it contains all vertices of your graph.
Yeah.
For example, this. So this one. So and this tree is contractible because, well, because of the, just because it is a tree.
Yeah.
So in the case, so the idea, so this is our discussion is kind of illustration the following fact that if pi1 of x is 0, then our x then 0 skeleton can be reduced to be a point. Okay.
But like you say that every segment is contractible. Yeah, so we can couldn't we say that for any CW complex, the one skeleton is just points?
No, for example, just for the circle, it's one skeleton is not a point.
But it's like the one cell of a circle is also a segment. And you say that segment is contractible?
Well, no. I say that. Sorry. Well, these segments is from one zero cell to another zero cell. So this is not a loop.
But for this example, which is 1 point with like 3 loop here.
So can you, well, can you highlight what example?
No, I don't know how to write on this board.
Okay, so let me try. So this one, or this one?
And the middle one.
This one.
Yeah.
So it's kind of flower. Okay, so and the question is,
why the loop here is contractible?
well, this is because pi1 of x is 0, because every loop in your space is homotopic to the constant map.
Yeah, so it's just not homotopic, but not contractible.
Yeah, but well, okay, so you can take your homotopy and contract with, so you have some homotopy. This means that you have a map from the cone of S1, where S1 is just this one, this circle. So you have a map from this guy to X.
Yeah.
So, and this is your homotopy of this guy to a point, and then you can extend this homotopy to whole X.
Sorry, what do you mean?
I mean, okay, so what does Borsuk lemma tell you? So you have, if you have pair of two of space and well, of CW complex and its CW subcomplex.
Yeah.
So then if you have any map from this pair to, okay, for simplicity, to any space Y,
Yeah.
and you have homotopy of this map to on A. So I mean, you have, okay, so I'll draw it here. So sorry. So you have a map to Y from is X, this is A, and you have homotopy from on A to Y, then you can extend it to the homotopy on whole X. Yeah?
Yeah.
Okay, so let me take for this pair just X and this one circle. And for Y, I'll take just X. Okay?
Okay.
So I have a map that is identity map from X1 to X.
Okay.
So now, because of pi1 of X is 0, there is a homotopy well, homotopy map from S1 cross unit interval to X such that it contracts, such that S1 on the, S1 cross 0 maps identically to this kind of this loop, okay?
Okay.
And S1 cross 1 maps to, maps to this point, to the base point. So this map can be factored to, so this is actually, this is the homotopy that I want to extend. So I don't need the con. So now I want to extend this homotopy. And on the top level of the extension, my circle, which is this circle, will maps to the point. So this means that I have constructed the homotopy from X to itself that contracts S1. Okay.
But so in this way, for any subcomplexes A, if A is non-homotopic, then X is homotopic equivalent to X quotient A.
Sorry?
So like if we follow your argument, then for any non-homotopic subcomplex, we call it A, then X is homotopic equivalent to X quotient A.
Yeah.
But that's not true. It's one of our homework. That's not true. This is true only if maybe not only if A is contractible.
Okay, so just yeah, but just 1 second. Let me.
Wait, sorry, don't we know that this is false? Because we can give S2 a CW structure with 1 cells in it?
Yeah, but you can always, but still it is homotopy equivalent to the
oh, you're right. Okay.
one with.
Okay.
Just. Okay, so I guess I can found the difference between these two. Well, just let me think for a second.
Yeah, and I think I can raise an example for this. Like a disk is not homotopic equivalent to a sphere, right?
Of course.
So if we take X to be a disk, and the X quotient S1 is a sphere, they are not homotopic equivalent.
Well, but wait for a second. I don't claim that. Okay, so I don't claim that in my case, X is homotopy equivalent to X X over S1. So I don't claim that if I take the quotient by this S1, it will be the space that I obtain will be homotopy equivalent to X. Okay, so I claim that I can contract. Well, I claim that I can contract that this S1, but not kind of take the quotient by it. Okay, so the difference is the following. So as you said, take the 2 disk, yeah. So my argument that I can always kind of contract this S1, and indeed I can since D2 is homotopy equivalent to a point, my homotopy is just the contracting of the 2 disk. Okay. This is taking. I'm not taking the quotient. But indeed, if I take the quotient by the boundary circle, it will be to sphere, and it is not homotopy equivalent. But I can always contract this this S1 inside my my X. So here my argument is the following. It was, I guess, it was one of the previous home sets. Let me see for just for a second. I guess in the indeed this is one of the arguments in the problem 4. I mean, so if I have 2 maps F0 and F1 such that they are homotopic from Y to some space X, then if I take the cone of this map, namely if I take kind of disjoint union of X and cone of Y and glue it by the bottom side of my cone, okay.
Okay.
F1, then and F0, then the spaces that I obtain are homotopy equivalent. Okay.
Okay.
So and my argument is exactly the same. So I take. Okay.
Yeah, I see.
So I'm. Yeah. Okay. Thank you for your question, and thank you for your kind of our discussion. So yes, indeed, I don't take the quotient by this circle, but instead I'm kind of use this argument and construct the contraction of this S1 inside X. Okay, so are there any questions?
No.
So I guess it is time to stop. So well, you can use the exactly the same argument to prove that that in this case your K skeleton is a point. Okay.
Yeah, can we also use the fact that the quotient of the K+1 skeleton by the K skeleton is wedge sum of spheres?
Well, of course, but how does Well,
And then you can use the long exact sequence with k skeleton, the quotient, and the k+1 skeleton. So then there has to be
Well-
0 spheres.
so, but for what you want to use your? Sorry.
I guess I want A to be the k skeleton, and then that lives inside the k+1 skeleton.
Yeah, of course. This is the quotient is wedge of spheres, but how
And
does
then I guess we need to show that this is isomorphic to the homology of the quotient.
well, okay, suppose we've done.
Okay, then we'll have an exact sequence of h, y goes to there, goes to A.
Yeah, okay.
And kind of by our hypothesis, this is 0 and this is 0. So this has to have 0 spheres inside it.
Well, but by what hypothesis we have?
So we know that
Well, I mean,
I guess
it is not true that if your whole space has 0 homology, then it is not true that it's any of its skeleton it has 0 homology.
Yeah, I guess you're right.
Okay, for example,
Okay.
you can just disk and its
Yeah.
boundary. So
Okay.
okay, so I will check your kind of homeworks on the weekend and send you the corrections by an email. So please please send me the current homework by an email in any time you want. But one thing I want to ask you, just please just kind of use theme of the letter kind of topology 2 homework. Okay, so it will simplify me the way to find the letter afterwards.
You mean the subject for the email?
Yeah.
Okay.
So okay, thank all of you. So I will send somewhere the link to the to the recording of this seminar, so you can look after if you want to. Okay, so for now it is all.
I have a question.
Yeah. Okay.
Professor Susinski has not sent yesterday's lecture yet, right?
Sorry.
Professor Susinski has not sent yesterday's lecture.
Well,
it is online.
Sorry?
It is online.
Ah, okay. Where?
I can, just a second, I can send you the link.
Yeah, I got it. Thank you so much.
yeah, and yeah. So but where it is? So okay. So I guess the recording of this seminar will be somewhere there. But I guess you, well, I guess in few days someone will send you kind of the link to the page where you can find all the Math in Moscow materials for the classes you take.
Mm-hmm.
Okay, so thank you all for coming. Something like.
Thank you.
Okay, so bye.